Okay, this is page 16 in our notes talking about the chloride anomaly. So chloride anomaly, basically, if we have entities that are present in aqueous solution, okay, is sodium chloride. Okay, the entities we'd have is sodium, chloride, and water. Okay, if we use our redox table, like in our data booklet, okay, on page 7, our strongest oxidizing agent's water, and our strongest reducing agent would also be water in this case, because chloride's so high up and um, sodium so far down. Okay, so the overall reaction in this case would just be at our cathode, the water reaction, when water is a strong or is our oxidizing agent, and then at the anode would be when water is our reducing agent. And so that's what it looked like. Okay, but chemists know, however, that by making the concentration of chloride ions high, the reaction will actually favor the formation of chlorine gas. So they found this out and they called it the chloride anomaly. So even though chlorine is above water as the strongest reducing agent, so here's chloride and that's water. So you'd think that water would be our strongest reducing agent. Okay, this is the one exception, the chloride anomaly. When the chloride has a high concentration, it becomes the strongest reducing agent and not water. Okay, and so this is what the reaction that would then occur in those cases. Okay, we'd still have water as the strongest oxidizing agent at our cathode, but now chlorine or chloride is our strongest reducing agent, which produces chlorine gas. And the electrons, here's the overall reaction. It has a really low or a really high amount of voltage that we have to overcome. And so we need that power supply. So this is kind of what happens as we have our sodium chloride being dissolved in this reaction. We get it's producing H2 gas and chloride gas. Again, they just discovered this by doing experiments. Another thing that they found is that in a lot of aqueous reactions, water has more positive reduction potential, so really is our strongest oxidizing agent. Like so, in that last case, with sodium and chlorine, okay, water became the strongest oxidizing agent. Okay, but what if we want metal cations to be oxidizing agents and undergo reduction? Basically, if we want to produce more of those metals. Okay, and so the production of strontium metal is an example. Okay, most often these ions are found in compounds. So if we had like strontium chloride. Okay, to produce strontium solid, we need to use a liquid form of the compound, so water is not present. Okay, so if it were present, it would become the strongest. There would be a stronger oxidizing agent than strontium. So we need to get rid of the water. So one way to do that is to basically melt, okay, our compound. So like if we have a molten salt electrolysis, okay, this is where the metal cations move to the cathode and are reduced to the metals, and the non-metal anions move to the anode and are oxidized into non-metals. So the example here, the electrolysis of molten sodium chloride is an important industrial reaction. So instead of having like aqueous sodium chloride, we have no water involved. We just melt down sodium chloride, so we have Na positive liquid and Cl minus liquid. They become our only possible oxidizing and reducing agents. So then what's happening at our cathode, we're making more sodium metal. And at our anode, they were making chlorine gas that can be pulled out. Okay, so electrolysis of sodium chloride is the basis of an important industrial process called the chlor-alkali process. Okay, most of the chlorine and sodium hydroxide that are used commercially are produced by this process. And so again, it's just electrolysis. Molten salts means we're just melting down that salt, whatever it could be, so that water doesn't interfere and become our strongest oxidizing or reducing agent. And so this metal refining electroplating kind of goes along similar basis. So electrorefining, he uses an electrolytic cell to form a high-grade metal at the cathode from impure metal at the anode. So example, like with copper, we put the impure metal here, Okay, and then we have a pure metal here. So, and the only thing in the solution would be copper 2 plus. Okay, and I guess it'd have some sort of negative anion. Okay, and so it's pulling out just the copper and producing pure copper on this side at our cathode. Okay, and then anything that's like in the impure copper would become a sludge down here. Yeah, and the electrolyte would have, we need to have that copper 2 plus, and then we'd have like an acid or something to help the reaction go through. Okay, electroplating is another important process. Electroplating, okay, is a common technology that is used to cover the surface of an object with a thin layer of metal. So a lot of jewelry is made this way. Pure gold's super expensive, but if you want to make a ring that looks gold, you can take a cheap piece of iron or whatever, and then put a layer of gold over top of it. I'll post a video kind of showing electroplating and the process of how you do it. We usually do a lab kind of showing electroplating and electrorefining, okay, but since you're at home and stuff, we can't do that lab. So I'll just post a video. Hopefully you're able to watch it and then kind of go over that. All right, we'll continue with cell stoic on the next video.